All right, this is T45, the second derivative test, a continuation on that, which we've already talked about. It says in the box up here, suppose f double prime of x is continuous on an open interval that contains c. All this is saying is that suppose that you have f prime of x, and you have some interval where this c value is on the line in between that interval. Let's just assume that. All right? So for part A, it says if f prime of c is equal to 0. Note that they're talking about f prime, all right, as opposed to f double prime. So if the c value, which is on the interval, if I plug it into f prime and get 0, I know that this represents a critical value. So c would be a critical value of the derivative. So that means that c is a critical value there, and f double prime of c. So if I take that same c value and plug it into the second derivative, if it's greater than 0, I know when f double prime of c is greater than 0, that means that it's positive. Well, what does it mean for f double prime to be positive? Well, that means that the function is concave up. Remember all of that we discussed. So basically they're saying if I have a second derivative and some value for c, which we know is the critical value of the first derivative, and if I plug in c into the second derivative and it's positive, which means that the function is concave up, all of that says that I have a local minimum at c. And let's think about why that's the case. Well, we're saying that here is c. That's my critical value. So that means that I have some type of hump there on my function, right? Well, if I put a point right there, I know that that critical value is saying that it's a hump. They're saying that f double prime of c is positive, so it would be concave up at c. So that means that c would have to be a minimum, because c was that critical value and it was concave up at that c. Now, part B is kind of saying the same thing, but it's changing up certain values. It's still saying that f prime of c is equal to 0, so it's still saying that c is a critical value. But here, f double prime of c is less than 0. That means that it's negative at c. So that means that the function f is concave down, so c down, right? So they're saying that I'm going to have a local maximum there. So that graph, kind of similar to what we drew here, if this is c, and I have some point, I'm saying is that hump on the function. This would be the function, right? So they're saying that f double prime is negative, so that means it'll be concave down. So if the function is concave down and c is a critical value, c would represent a max here. So this would be a max. This would be a min over here. So that's what all they're saying. So I have to, in order for me to use the second derivative test here, how they want me to use it, I need the second derivative and I need the critical value, which they're calling c. So let's look at the example here. Example 1. Critical values for a given function, f of x, are x equal -1, 0, and 1. So they gave me the c's. These are my c's. And they also going to give me the second derivative. Given the second derivative equals f double prime of x equals 4 minus 12x squared, determine if any of the critical values are local extrema. Extrema just means max or mins. So they want to know where any one of those values for x that they're calling the critical values, Will they be maxes or mins? So all we have to do is plug it into the second derivative. So f double prime of, let's try -1, equals 4 minus 12 times -1 squared. If I work all that out, that's going to become a -8. So we have a -1 being the critical value, because they told me it was. And at f double prime of a -1, I see that I have a negative number. So that means that my function will be concave down at -1. So that means that I have a max, a local max at -1, at x equals -1. All right? And I'll do the same thing with 0. So f double prime of 0, that will basically be 4. So I know 4 is positive. So I'm concave up there, so I have a local min, because that's following part A at x equals 0. If I try 1, f double prime of 1, if I work it out, it's going to come out to that same -8. So I have a local max at x equals 1. All right? So that's basically it. All right, so example 2, critical value. So this is basically the same thing as example 1, critical values for a given function f of x. So they gave us the critical values, gave us the second derivative. All we do is plug it in, plug in the x value. If I get a negative number, that means that it's a local max. If I get a positive number, that means that it's a local min. What if I plug it in and I don't get a positive or negative number? That means that I'm either getting 0 or it does not exist, right? So if that's the case, you cannot determine. That means that if you get 0, it's not a max nor a min. So I think this is one of them. Let me see. If I plug in -2 here, f double prime of a -2 is equal to, it's going to end up being 4 minus 4 over 4, so that's 0, right? Well, 0 is neither positive nor negative, so there's -2 is no max nor min. It has to come out to either positive or negative. And if I do the same thing at 2, same thing, I'm going to get a 0. So that means if they want us to determine if they have any, well, if -2 and 2 are my only critical values, and I plug it into the second derivative and I'm not getting a negative number nor a positive number, then that means that the answer here is there are no local extrema for this function. So the critical values have to yield a positive number in the second derivative or a negative number in the second derivative in order for me to come out with a local max or min.